Welcome to this ABSciX webinar, where we will be discussing high-throughput technologies for clinical research and toxicology applications. Thank you for joining us today. The high-throughput solution from ABSciX that I will be describing to you in this webinar combines the LC multiplexing capabilities of the MPX2 SP high-throughput system and the power of the high-resolution accurate mass 4600 TripleTOF system. The MPX-TF software allows for easy conversion of singleplex methods to an LC multiplexing workflow, and we have new software that provide innovations for TripleTOF data processing, which will also be described in this webinar as part of this overall high-throughput workflow. So we really can combine the power of the high-resolution accurate mass technology with the dual stream flow of the MPX system to significantly increase throughput and meet the demands of a high-throughput lab. I would like to begin by talking about the capabilities of the high-resolution accurate mass 4600 TripleTOF system. The technology is based on a hybrid quadrupole time-of-flight platform and allows the acquisition of highly sensitive full-scan MS and MSMS spectra with high resolution and mass accuracy. The technology allows targeted and non-targeted screening to be performed in a single LC-MS run. High-sensitive full-scan MS and MSMS spectra can be measured accurately and reproducibly for quantitation of targeted compounds, as well as allowing the confident identification of knowns and unknowns from the same injection, with accurate mass, library searching, and most significantly, retrospective data processing. The ABSciX TripleTOF 4600 system really does combine the best of both worlds by taking the ion path innovations of the triple quadrupole 4500 system and combining it with the accelerated TOF analyzer. So therefore we really do get the combining of technologies where we have the qualitative analysis power of a high-resolution accurate mass analyzer and the quantitative speed, sensitivity and linear dynamic range of a triple quadrupole instrument. TripleTOF technology really does provide nice advantages when it comes to screening, as it allows setting up and running simple generic methods. Here are two examples of screening workflows performed on the 4600 TripleTOF system. On the left, we have an untargeted data acquisition approach through an independent data acquisition setup. So in this method, we have a TOF MS survey scan that detects all molecular ions. And if an ion reaches an intensity threshold that we've already set in the software, then an accurate mass product ion spectrum for that ion will be triggered. So both MS and MSMS data for the compounds in the sample will be acquired to aid in confident identifications. On the other hand, if we look to the right, we have a targeted approach set up. And so this is where we have an experiment containing multiple MSMS scans of different precursor ions. And then these are looped together for a multiplexed assay. And this is known as MR/HR, which is multiple reaction monitoring high resolution. And so this experiment ensures low-level compounds of interest are detected in dirty matrix. And we have the extra selectivity of MSMS, which removes the interferences from the extracted ion chromatograms. And so this ensures acquisition of high-quality MSMS data for library searching. So as I alluded to in the previous slide, there are a number of accurate mass screening workflows that we can perform on the 4600 TripleTOF instrument. And really, the data acquisition itself is relatively simple when performing it on a TripleTOF system, as there are only a few experiments that we can perform on a QTOF type instrument. and it is really the data processing that is the key component to an accurate mass screening workflow, because really we have to be making sense of all of that data that we're generating from the acquisition. So let's start on the left hand side of this slide with the targeted data acquisition approach. So this can be done by the experiment I described in the previous slide with the scheduled MRM-HR workflow, which entails using multiple looped product ion scans for targeted precursor ions, and each precursor ion is only monitored during the compound's expected retention time. So this means that the number of concurrent MRMs decreases, which allows monitoring for more compounds and at the same time maintains a cycle time and dwell time. But the overall effective duty cycle of every compound increases, and this allows us to maintain analytical precision. So this approach really ensures MSMS data is acquired for the targeted compounds and also enables high selected extracted ion chromatograms of the characteristic fragment ion for each compound. And it also ensures that there is a generation of quality MSMS spectra that can be used in library searching, and this can be added to our identification confidence for our targeted compounds. So if we now look to the right of the slide, we can perform a non-targeted data acquisition using the TOF-MS IDA MSMS approach that I described in the previous slide. So we have generated this data that can be mined in two ways. The first one is a targeted approach, which, as you can see in the middle of the slide, allows us to screen and quantitate as well as identify targeted compounds based on retention time and accurate mass, as well as performing MSMS library searching and automatic formula finding. So providing a nice approach for analyzing our targeted compounds. On the right, we can perform a non-targeted data processing, and this allows us to mine or search for our unknown compounds. And as a way of actually narrowing down to the significant compounds, we can actually perform what is called a sample control comparison. And so this is using the software which highlights the differences between your sample and your control. We can then identify our unknowns based on accurate mass, isotopic pattern, adducts, and MSMS data using formula findings as well as automatic ChemSpider searches. And we can also perform fragmentation prediction tools to aid in our structural elucidations. So this slide really demonstrates and summarizes the nice screening approaches that can perform on the 4600 TripleTOF system for both our targeted compounds and for unknown compounds and unexpected compounds. So we talked about the power of high-resolution accurate mass technology, and how can we actually use this in a high-throughput environment. So if we have hundreds of samples per day that we want to be analyzing, a way in which we can increase the throughput of the system is to multiplex the LC upfront components to the high-resolution accurate mass system. And so in the end, we're easing the pain of the high sample volumes. So how does the multiplexing of LC systems work? So in the example provided here, we have two LC systems that are parallel, and they go into a single mass spectrometer. And so the idea is that we want to maximize the time that the mass spec is acquiring useful data. So we want to minimize the MS idle time during, for example, the LC column equilibration. And in the end, we improve the overall LC MS throughput by doing this. So we achieve this by staggering the injections from stream 1 and stream 2. So we would start an injection on stream 1, but the mass spec doesn't start acquiring until just before the first peak is eluting on gradient 1, at which point we can actually start an injection on stream 2, so that when we are acquiring the last peak on gradient 1, we're already at the point on gradient 2 at which the first peak is eluting. So as soon as the mass spec stops acquiring from stream 1, it then starts directly acquiring on stream 2. So we're using the mass spec 100% of the time that's acquiring useful data, and improving the overall LC-MS throughput. And so we carry on this process until all our samples in the assay or sample list are acquired. So the MPX2 system is a product that delivers up to 2 times increase in sample throughput by optimizing MS uptime through the use of 2 LC streams and 1 single mass spectrometer system. And so in the MPX high throughput system we have a couple of configurations. One of them uses all Shimadzu components with 2 Shimadzu autosamplers, and the other one you can replace the 2 Shimadzu autosamplers with a single CTC autosampler. And both these configurations we can perform an online SPE versions of these configurations as well. So the products that we have under the MPX2 systems include the first one, which is the MPX2 high throughput system, and these are 2 LC systems going into 1 mass spectrometer. The 2 stands for 2 LC streams and the MPX stands for multiplexing. And then we have the MPX2 SP high throughput system, and that is the online solid phase extraction with the SP standing for solid sample preparation. And then we have the driver or the software itself that is in control of the LC system, and that's the MPX-TF driver 1.0. So this slide shows the 2 configurations that I described previously. So on the right we have all Shimadzu components, and so we have for each stream 2 isocratic pumps that are joined together by a mixer to give us our gradient pump for stream 1, and then we have the same for stream 2. And then we have a column oven that's shared between the 2 streams, and then in the Shimadzu configuration we have 2 autosamplers, one for stream 1 and the other one for stream 2. And then we have a loading pump that is used to deliver the sample from the autosample onto the column, and then so that this is shared between the 2 streams, and so we have a switching valve that switches between the loading pump and the gradient pumps. So that's the Shimadzu components on the right, and on the left we can actually replace the 2 Shimadzu autosamplers with a single CTC PAL autosampler, and the advantage that gives is that it's an open access system, so we have 2 injection ports, one for stream 1 and the other one for stream 2, so samples can be delivered to either stream 1 or stream 2 in this configuration from the same single autosampler. So some of the key features of the MPX system includes a single vendor solution, also a single point of control software for the entire system. We have an audit trail traceability from a single software package for compliance issues, and then we have a nice on-screen method editor that allows for the easy conversion of singleplex experiments to a multiplexing workflow. And all the technology is based on the high pressure system pumps from Shimadzu. So really we have the workhorse and the software that actually controls all the systems, and that's the MPX-TF driver 1.0. And this is the MPX software version that supports the running of the MPX to SP high throughput system with the TripleTOF 4600 LC MSMS system. So this slide shows the method editor of the software and really demonstrates how easy it is to convert a singleplex method to a multiplexing workflow. So the software, as you can see, has all the same parameters as you would in a singleplex experiment, except there's a couple of differences, and that's where we want to identify the time of the gradient at which the mass spec will be acquiring. And to aid us to define that area, we can actually upload an example chromatogram. And so you can see in this blue shaded area, that defines the area of the chromatogram the mass spec will be acquiring. And we can see that our peaks and the time that the peaks are eluting during the gradient. So we can highlight that area of the gradient to which the mass spec will be acquiring. And then we have a nice gauge here to just demonstrate at which point we'll gain 2 times increase in throughput. So all the other functionalities are the same, so incorporating our gradient conditions as well as our autosampler conditions. And then we have our wash options down here which we can customize as well. And a nice feature is this error recovery policy, which allows us to, if one of the stream fails, we can actually transfer the samples onto the stream that's not failed. So this slide just shows the status pane of, or the workspace of the MPX system, and so this just allows us to monitor the system, see the pressures of each of the streams, stream 1 or stream 2, as well as the loading pump. And then down here we also have the option to equilibrate from different methods. So we can actually use this system to acquire different or use different methods on opposite streams. And so this functionality here allows us to equilibrate the opposite streams with different methods. So this just demonstrates the flow paths. Just on the left here we can see the flow path, and the actual gradient stream selector valve allows us for stream 1 to go into the mass spectrometer, and then on the right we have the selector valve that selects so that the mass spec is acquiring from stream 2. So now I just want to show you some examples of using the multiplexing technology combined with the high resolution accurate mass TripleTOF solution. So the first one I want to show is more of a comprehensive drug screening assay, and so this is more just improving the overall timing of such a comprehensive assay. So this slide shows the experimental setup for this comprehensive drug screening assay. So it was performed using a kinetics column, C18, and the gradient was a 6-minute gradient, but we used a 4-minute acquisition window, and we performed a spiked calibration curve for this analysis, and we used an IDA approach, this time using a TOF MS survey with a 70 millisecond accumulation time, and we triggered up to 20 dependent TOF MSMS scans using 25 milliseconds accumulation time. So that in these experiments we also use a collineage energy of 35 volts with a collineage energy spread of 15 volts, and this helps generate nice product time spectra for using in library searching, and using a good collinear energy spread in order to obtain low and high energy fragment ions. And then the data processing itself was used the MasterView software with Multiquant software. And I'll be detailing some of the MasterView software later on in the slides. So when it comes to increasing the throughput of a comprehensive drug screening assay, it is a little bit different because you want to be able to get the coverage of all the analyte classes. And so this pretty much means that you can only really probably gain time by not acquiring the equilibration time of the gradient. So with this particular example, even though it was a 6-minute LC method, we were only able to actually reduce that to 4 minutes. But overall that gives a nice increase in throughput. For example, here we've performed 53 injections and we get an hour and a half savings in time. But we're sacrificing a little bit on the speeds, but the fact that we're getting very good coverage here that allows us to both target it for our unknown as well as our, specifically for our targeted compounds, but we also want to see if there's any unknowns or unexpected compounds there. So we have to be acquiring most of the gradient to allow us to do that. But with this workflow, we're able to both identify the compounds, but at the same time quantify them as well from the same injection. So now I want to demonstrate results of an experiment in which it was purely a targeted approach, and it was meant to be a very fast screening approach. So this is the experimental setup, and this time, instead of using the IDA approach as I showed previously, we used the MRMHR approach. So this was just used a small separation using a guard column, and the gradient time was 0.8 minutes. And effectively, in the end, we had a less than 50-second injection to injection time. So this is using the targeted, dedicated looped TOF MSMS product ion scans for 41 targeted compounds. And for this experiment, we used an optimized clinic energy for each of the compounds, and we did perform one TOF MS scan in the first part of the experiment at 50 milliseconds, and then the rest of the targeted TOF MSMS product ion scans had a accumulation time of 10 milliseconds each. And again, we used the data processing was performed using MasterView software. So this slide shows the results of such an experiment. So again, we were able to achieve less than 50-second injection to injection time, but we were able to screen and identify confidently 41 targeted compounds based on mass error, isotopic matching, retention time, MSMS library searching, as well as formula finding. So we're using all these criteria for our confidence in identifications. And this slide just demonstrates a very quick 2-minute screening method that has been halved from its original time. And in this case, we're looking at 33 drugs in a neat mixture, but just to show the capabilities of increasing the throughput by up to 2 times. And we're still getting the points across the LC peak. So this is just for a K2 spice metabolite compound, as well as another JWH compound, just showing the number of points that we can get across the peak with the speed of the TripleTOF 4600 technology. So largely up till this point, I've talked about acquisition aspect of this high throughput workflow and the ability to increase our throughput by up to 2 times using the MPX technology on the TripleTOF 4600 system. But with such an accurate mass workflow and complexity of such data acquired, we really do require a powerful data mining tool. So we have such a tool in the form of the MasterView software that allows getting to our answers very quickly in an intuitive, nimble and sensible way. The MasterView software achieves this by managing large lists of compounds and performs extracted ion chromatogram calculations, both targeted and non-targeted peak finding operations, as well as library searching. So I'll first of all demonstrate using this new software in a targeted screening and identification approach, as well as demonstrate performing quantification from the same data. So after opening a data file in the PeakView software, the MasterView software is launched from the PeakView toolbar. The XIC table that's opened up in MasterView contains a number of columns with values that can be edited, including name, formula, adduct, retention time, and more. So to define an XIC, a mass must be entered, and this can be done by directly editing the cell, having the software calculate the value based on formula and adduct provided, or by pasting values from a spreadsheet, and the generated XIC list can be saved for future processing. The confidence data for each compound identified is visualized using a traffic light system which can be user definable. This slide shows the user definable confidence levels that we can use within the MasterView software. So we are really basing our identifications and confidence in identifications based on many criteria, and these are mass error, retention time, isotopic pattern matches, library hits, and automatic formula finding calculations. So when we perform an extracted ion chromatogram calculation, we base our identification on 5 criteria, and each criteria can set the level at which it will show a good match. For example, a green tick is for a good match, a less likely match will be yellow, and an unlikely match will be highlighted in red. So to perform an extraction, all we have to do is actually click on the Show XIC icon, and the MasterView will calculate the extracted ion chromatograms as well as evaluate accurate mass, MS and MSMS spectra for identifications. This slide shows the result display from the XIC Manager, and so we are basing our identification criteria on the mass error, the retention time, the isotopic pattern match, as well as MSMS library purity score and the formula finding. So we're using 5 traffic lights to which we are basing our identifications on. We can actually customize what compounds will be displayed in the software, and so for example in this example shown, I have asked the software to only display to me compounds that have been identified with all 5 green traffic lights, and this is customizable. So if we want to display compounds that didn't get 5 green traffic lights, then we can do this as well. So this slide shows the integrated spectral view. So for any compound you can select and look at both the acquired TOF-MS and TOF-MSMS data. So on the bottom left we have the TOF-MS spectrum for this compound that's been highlighted, and we overlaid from the acquired spectrum is the theoretical isotopic pattern, and so that's a nice visualization of the closeness of the match between the acquired spectrum and the theoretical isotopic pattern. And then on the right we have the TOF-MSMS of that compound, and this is a mirror view of the spectra for an easy comparison between the acquired spectrum and that's been performed in the library matching and has matched the spectrum in the library. So again, we're using a lot of criteria here to identify our compounds, and the visualization using the mirror view of a spectra for easy comparison on the library searching is just one of those criteria. This slide shows the automatic formula finding that I described previously. So the formula finding uses high resolution accurate mass information of the molecular ion, adducts, isotopic pattern and fragment ion information to empirically calculate potential molecular formula, which can only be achieved by combining all available MS and MSMS data. A couple of functionalities of the software are shown here. So one of them is the ability to generate reports with the identified compounds, and the other one is the ability to export information to multi-quant software. So that allows us to generate calibration curves and quantify the identified compounds. This slide shows the report generation capabilities of the MasterView software. So we have a button that is pressed and we can automatically generate reports. And so the reports can be obtained in a Word, CSV or PDF format, and report templates can be customizable. This slide shows that as well as identifying the compounds, we can also quantify the compounds from the same workflow or the same injections. And so here we have the multi-quant software that has allowed us to generate calibration lines and quantify the identified compounds. This slide shows the comparative screening workflow, so we can actually compare our sample to a control. And in this particular example, we're actually identifying a sample to a 10 nanogram per ml standard. And so we only want to be identifying compounds that have a concentration higher than this cutoff level. So in this particular example, we've only identified a couple of compounds that have 10 nanogram ml concentration or higher. And so they're the only compounds that will be extracted and highlighted in green in this particular workflow. So having concentrated on the targeted approach, I now want to describe how we use the software in general unknown comparative screening and to identify our unknowns or unexpected compounds. And so with this workflow, it's pretty nice setup using the MasterView software because it allows us to do both the simultaneous targeted screening and identification of unknowns. So as previously, an unknown sample as well as a 10 nanogram per ml standard are opened up in the PeakView software. And a very nice feature of the software is the ability to do simultaneous targeted and non-targeted peak finding. So we can use an XIC list containing targeted compounds and perform an extraction, but at the same time look for unknown peaks. So this example here shows a small list of targeted compounds we're initially screened for, but in the end we get our result as the unknown peaks are added to the XIC list after the extraction. So we can get information on our targeted compounds, but at the same time data mine for any unknowns or unexpected compounds. So first of all, we look at any targeted compounds that might have been extracted. And so this one shows that our unknown sample has a few compounds that are higher concentration than the cutoff 10 nanogram per ml standard. And so again we get our comparison between the sample and the control. On the left we have our TOF-MS data, the top TOF-MS being for our unknown and the bottom one for our control. And then on the right we have the TOF-MS data. So in this particular example we had 5 compounds from the original target list that were identified that were above the 10 nanogram per ml cutoff concentration. And each compound were identified with 5 green traffic lights. So this gives us high confidence that these compounds were actually in this sample. And again, just to show the confidence and the criteria that we're basing these identifications on. So again, we're showing the sample and control comparison, but we've been identified these compounds within the sample based on mass error retention time, isotopic matches, as well as MSMS library searching and formula finding results. So after identifying our target compounds, we can now look at the list and re-evaluate any unknowns or unexpected compounds that might have been present. So this slide shows the unknown structural elucidation workflow. So for example, we've had an unknown or unexpected non-targeted compound that has been automatically added to our original XIC target list. And the MasterView software automatically empirically calculates any potential molecular formula for the extracted mass of the unknown compound. And that is using both acquired MS and MSMS data for this unknown. So we're pretty confident in the calculations the software is performing. So in continuation of the unknown structural elucidations workflow, we can actually, from the XIC list result table, we can actually open up a ChemSpider session, and so this allows us to identify potential structures that match the calculated formula. Once a ChemSpider session is opened, we get a list of potential structures from the ChemSpider website that match the formula that has been calculated by the MasterView software. And so you can see we get a lot of structures that match the calculated formula, and this really highlights the importance of MSMS acquisition for unknown analysis. So the full scan high resolution results give chemical formulas, but they do not identify compounds. So to accurately identify compounds, MSMS fragmentation patterns are required. And that's actually what we do in the MasterView workflow. So in this pane, that's all integrated into the one pane. So we get structures from the ChemSpider that are linked to the MSMS data. So the software performs ion fragmentation prediction calculations and matches fragment ions in the spectrum to fragment ions that would be obtained from the selected structure. And so in this particular example, 7 of the 9 peaks matched with 83% explainable MSMS fragment ions for the MDPV cathinone designer drug structure. So we can tentatively identify this unknown compound as a cathinone designer drug structure. Within the software, we also have a link to the ChemSpider website. So by having this link, we do have the advantage that this allows searching based on the number of references and data sources. And so this helps really narrowing down to the structures that match the unknown compounds we've identified. So in this presentation so far, I've hopefully demonstrated the power of MSMS, but really MSMS is very important in when it comes to identifying competently your unknowns. The TripleTOF solution provides a strong means in which to generate MSMS data. And so this, in combination with the multiplexing of LC systems, allows the reduction in possibilities of false negatives and positive results in a high-throughput screening analysis. So in the case of false negatives, that is normally caused by low sensitivity systems and ion suppressions with co-eluting matrix or high-level analytes. So really sample preparation and or LC separation are key to alleviate these problems. So this makes multiplexing LCs an important aspect of a high throughput system. Another cause of false negative is an isotope ratio difference and mass accuracy between theoretical and acquired data caused by an interfering substance, which, if we rely on single MS alone, could cause a false negative. But if we are able to generate an MSMS spectrum, then we can alleviate the possibility of this false negative by having a good library match and identification. When it comes to false positives, isobaric compounds or other interferences with the same retention time can cause such a phenomenon. Also, the interference from dirty sample matrix or column can cause a false positive result. But if we can use LC separation as well as using the specificity of the extraction of the fragment ion of our compound in our MSMS data generation, then this can also alleviate the potential for false positives. On the other hand, another aspect that can cause a false positive is high-level sample carryover, which can be alleviated with a good LC system using an autosampler that effectively removes the carryover. So really we have a powerful solution with the combination of the MPX system and TripleTOF 4600 system. We have the capability to multiplex liquid chromatography systems and at the same time have a system that has the speed to acquire many MSMS spectra a second, and then so in combination with the high throughput LC separation and generation of MSMS data, we can acquire specific fragment ions of our compounds, and we can have an overall system that can drastically reduce and alleviate the possibility of false positives and negative results. So this slide actually demonstrates how false negative rates can be reduced with the acquisition of MSMS data. So in this example we have an unknown sample that wasn't hydrolyzed, and we performed a dilute and shoot. And as you can see, due to a co-eluting unknown compound, the isotopic ratio for this known compound was off, which could potentially cause a false negative conclusion. But because we generated MSMS data, we obtained a good library match to confirm that this compound was actually present. So this is just another example in which we have an interference that causes an isotopic ratio change, but because we generated MSMS, this confirmed the identity and eliminated a false negative conclusion. This slide shows that full scan resolution and mass accuracy alone is not enough, and MSMS is necessary for compound identification. As you can see here, structural isomers have the same formula and exact mass, and without MSMS we would not be able to distinguish between these two compounds. With the acquisition of MSMS data, we were able to do library searching and confirm and confidently identify which compound this was from the sample. So from this webinar, hopefully I've been able to show you the strength of the TripleTOF system and its ability to collect high resolution and accurate mass MS and MSMS data in a single injection. And so we're able to do qualitative screening and at the same time perform quantification and confirmation in a single injection. And really the PeakView and MasterView software are the key enablers of the workflow to get to the results. So full scan resolution and mass accuracy alone is not enough, and MSMS is necessary for confident compound identifications. And so high resolution results give chemical formulas, but they do not identify compounds. So to accurately identify compounds, MSMS fragmentation patterns are required. So with this technology of the TripleTOF 4600, labs can do their routine screening assays, but at the same time survey for unknown or unexpected compounds from the same injection. And so when we couple the MPX system with the TripleTOF 4600 LCMS system, we have a very strong and powerful workflow to perform drug screening. So using the LC multiplexing analysis, we can reduce the concerns of ion suppression and carryover, but at the same time allow for a high throughput screening analysis. That concludes our webinar on the MPX system with the TripleTOF 4600 system and its use in routine high throughput drug screening analysis. I would like to take this opportunity to thank you for your attention. Goodbye.